Now let's consider the ground state, and if you recall, we use the following notation: 0p, like this. If we act with the number operators n or also n tilde on 0p, we will get that the result is simply 0. This is because the annihilation operators contained in the number operators, in particular we are talking about alpha in and alpha tilde in, they will simply destroy the vacuum state. In this case, this specific example, where we act with the number operators on the vacuum state, the mass squared operator, so when it acts on the vacuum, the mass squared will give us 4 over alpha prime, 0, because the number operator will give us 0, as we said, minus d minus 2 over 24. And this is equal to minus d minus 2 over alpha prime 6, like this. So for d greater than 2, we get m squared less than 0, which means that the mass of this excitation state is imaginary. This particle is called a tachyon. So we get a tachyon. This is a troublesome particle, actually. You might have heard it in special relativity as a particle which travels faster than the speed of light. We won't linger on this particle any further. We will not focus too much on this particle. What is actually more interesting are the first excited states. So we will not, let's say, talk any further about the tachyon, but this is something which is predicted by string theory, in particular bosonic string theory. We are considering the bosonic theory because we are considering bosons. And if you remember, we are using commutation relations after all. So our theory can only be bosonic. It is also possible to extend it to fermionic theories, but it is not the point of discussion here in this course. And now, if we consider first excited states, we need to act with the creation operator on the vacuum to create something meaningful out of the vacuum. So alpha j minus 1, for example, we need to, so if we want to act with this operator, we have to be careful because we also need to act with alpha tilde I minus 1 in general. Why is that? So we need, if we act with this operator on the vacuum, we also need to act with this one. And the reason is simple, because we have the condition that the mass squared can be written in two ways, like this or like this. So if one state contains alpha j minus 1, it should also contain a similar version but with a tilde, because otherwise the mass squared operator will not give you any, let's say, unique answer. So it's very important that we make our theory consistent. And so the fact that m squared is given by two different formulas is also called the level matching condition. And this condition tells us that we should get the same result when we act with n or when n tilde. Otherwise, the theory would not make sense. So, as the first excited states, we can have something of the following form: alpha I, and here we will consider minus 1, alpha j minus 1 acting on 0p, acting on the string vacuum. By varying the indices I and j from 1 to d minus 2, so remember that our independent operators are d minus 2 for alpha tilde and d minus 2 for alpha. We realize that we have d minus 2 squared states, each of which has the following mass squared. So the mass squared can be written as 4 over alpha prime, and in this case we have 1, So because in this case the number operator will give us 1, since this is the first excited state, minus d minus 2 over 24. So as I said, this is due to the number operator. But now we have reached the point where we are forced to choose a value for d, the number of dimensions. And why is that? Well, we need to make sure that our theory is Lorentz invariant. And Lorentz transformations can be represented by means of d-dimensional matrices. So we have one dimension of time and d minus 1 dimensions of space. But the states related to the indices I and j are d minus 2 squared, which means that we could think of d minus 2 dimensional transformations. Is that so? Well, this seems as a very complicated issue to resolve, but luckily there is a way out. In order to see this better, let's consider 4 dimensions. 1 dimension of time and 3 dimensions of space. In this space, the complete set of Lorentz transformations is obtained by composition of 3 boosts and 3 rotations. The boosts are related to the transformations we saw in special relativity, when we go from one frame to a frame with a different velocity. So we change the momentum, basically. Since we can move either along x, along y, and along z, we have 3 possible boosts. And the same holds for rotations, right? You can think of 3 different rotation matrices around x, around y, and around z, and by making a composition of these matrices, you can get a generic, a very general rotation. Now let's consider first a massive particle, so a particle with a certain mass. For a massive particle, we can choose a rest frame in which for momentum p mu can be written as E0, 0, 0. So we can choose a rest frame because the particle has a certain mass. For example, we couldn't do so for a massless particle such as the photon. By the way, E is simply equal to the mass times the speed of light squared, mc squared. Now, it is quite intuitive to understand that the energy of the particle will remain the same if we make any 3D rotation. And we want to keep the same energy, want to preserve the same energy because we are interested in states with a given mass. So we preserve the energy by making any kind of 3D rotation. It's as if you take, for example, these 3 components of this vector, and this represents simply a point at the origin, and if we make any 3D rotation of this point, it will still remain a point. So this is something still intuitive, not rigorous, but you can understand why we are allowed to make any 3D rotation, but the state will remain the same. So it, let's say, underlies some kind of symmetries in our theory. And the rotations are described by the so-called special orthogonal matrices in 3 dimensions. This is a group, and it is called SO3, special orthogonal group in 3 dimensions. Now, consider a massless particle at this point. In this case, we cannot choose a rest frame. The best that we can do is to choose a frame where p mu is equal to E 0, 0, E, for example. So we cannot set this equal to 0. Why is that? This is due to the fact that in general p mu, for a massless particle, this is equal to 0. But this will imply minus p0 squared, and then we have plus the 3-dimensional momentum squared, in particular the mode squared of the 3-dimensional momentum. We set it equal to 0, so we get p0 equal to the mode of the 3-dimensional momentum. And we call it E, and we assume that momentum is directed along the z-axis. So basically, this is just the mode of p. And it is equal to E, so it cannot be zero. There must be some momentum due to the fact that the particle is massless. So here we have a vector along z, x, y, z, and this is mode p. Or if you want, we can call it, so this is the vector p, this arrow. Now, in order to keep the same energy and also momentum fixed, we can only rotate this vector around the xy plane, right? So we will be able to preserve momentum and also the energy if we rotate this vector along the xy plane. So basically this becomes a rotation, so it will belong to the group SO2 in 2 dimensions. This will be a 2-dimensional rotation. It's very important because now we can try to generalize it to d dimensions. In d dimensions, the symmetries of the massive particle are described by SO d minus 1 because we can choose a rest frame where p mu is equal to E 0, 0, dot, 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 0, and these are d minus 1 zeros, whereas for the massless particle, we have p mu equal to E 0, 0, dot, 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 0, E, where these zeros here are d minus 2. So here I'm assuming that momentum is directed along the last axis. This will be the d coordinate, so it will be directed along the axis of xd, the d variable. So it means that in this case we will preserve the symmetry with rotations of the kind SO of d minus 2. This is a fundamental result because in this case, so in the case of first excited states, if we want to use d minus 2 dimensional matrices, so remember that we have d minus 2 squared states, so it makes sense that the type of transformations that we can use are of this kind, SO d minus 2. They belong to this group. This is a fundamental result because in the case of, as I said, first excited states, if we want to use d minus 2 dimensional matrices, which are consistent with the Lorentz theory, so the reason why we are using these kind of transformations is because they are consistent with Lorentz theory. We can always think of a rotation as some kind of generalized rotation matrix. Therefore, we are actually forced to make these particles massless if we want to describe them. So these particles need to be massless if we want our theory to be consistent. So the first excited states need to be massless. This is very important, fundamental. Let me stress this. So this equality comes from the considerations that we made below. And this gives us an equation for D. If we choose D equal to 26, you can see that 26 minus 2 is 24. 24 over 24 is 1. And then you get 1 minus 1 equal to D. So it implies D equal to 26. So this is fundamental. It is not over yet because there are lots of other interesting surprises in string theory. But we see that in bosonic string theory, we are forced to make this choice, D equal to 26. And we will continue next time.